Hello, let's make a retro arcade racing game.
So in the classic retro arcade style, we've got a car moving into the middle of the screen and we've got bends on the track, and we can see how fast the car is moving because we've got lines scrolling towards us at different speeds. We can see the turning of the car because I've got very terrible sprites, my apologies for the crudity of the model. The mountains in the background scroll around as necessary to give us the illusion that we're turning round the bends. And the objective of the game is to get around the track in the fastest possible time. And there is actually some dynamics that affect this. So if we go off the track, we slow the car down artificially. And as I'm just about to cross the start-finish straight, we can see what lap time I clocked, and this time was 42.8 seconds. I'm sure we can do much better than that. If I attempt to go too fast around the corner, I'm pushed out to the side. So I have to use the accelerator quite carefully.
Unlike some of my other Code It Yourself videos, this one looks like there's a lot going on. But actually, there isn't, and I think this is really what this video is about, is we can take a really mundane, simple mathematical concept, but if we present it in an interesting way, it becomes a playable game. And as usual, we'll be doing all of this in the command prompts. This is all ASCII art, we don't need any third-party libraries to get us going.
As per the current trend of my videos, I'm going to be using the OneLoneCoder console game engine, which you can read about in the little link above. The game engine is a base class that we must inherit from and overwrite two methods, onUserCreate and onUserUpdate.
All this class does is wrap up the user input and display into the console, so I don't have to type it out for every single video.
All my int main function is going to do is create an instance of the class, in this case it's Formula1LoneCoder.
Please don't sue me, FIA.
And this time I'm creating a console which is 160 characters wide and 100 characters high, and each character is going to be 8 by 8 pixels. Let's start by getting some of the easier stuff out of the way first. So I'm going to draw a track, and of course this occupies the bottom half of the screen. So I'm going to take the screen height and divide it by 2. Then for each row, I need to break up the row into whether it's grass, clipping board, or road. So each character going across the console, we're going to classify as one of the other.
To make things a little simpler, I'm going to assume that the width of the screen is going to be in normalised space, so we'll have 0 for the left and 1 for the right, so the middle of the screen will be 0.5. This is useful because we'll probably want to scale things up depending on the size of the screen, but it also makes some of the mathematics a little simpler later on too.
So the first thing to establish when drawing the track is where is the track on the screen. I'm going to assume we're drawing it in the middle to begin with. So that's a 0.5 in our normalised space. I'm also for now going to assume that the road occupies about 60% of the screen. And so everything remains proportional. I can assume that the clipboard width, they're the red and white lines going around the track, I'm going to assume that they're 15% of the road width. And just to make the next section a little simpler, I'm going to assume that the road is symmetrical around its middle point. So actually I can halve the road width, and we'll see why this comes in handy now. As we're iterating across the screen column by column, it's important to classify each character as being grass, clipping board, or road. So I need to work out where those boundaries are in the x direction. So for example, I know that my grass begins at 0, but it will stop when we get to the middle point of the track, minus the road width, which is now half, and minus the clipping board width. I can then scale that into the screen space for the console. In a similar manner, I can work out where my left clipping board is. So it's exactly the same calculation, but I don't need to include the clip width this time. And because we halved the road width before, doing the right-hand side is the same now, except we're doing pluses instead of minuses. So we're exploiting the symmetry in order to make things simpler for us to do. Now we just need to colour them in. So we know that if x is greater than 0 and x is left than our nLeft grass variable, that we're going to shade that character green. And I'm going to use the draw function. So this is provided by the OneLoneCoder class, and all it does is take the x and y coordinates, and we can use the solid character to basically fake a pixel and we'll use the constant FG green for grass. Some of you may have noticed that actually Y represents 0 to screen height divided by 2. So that means we'd be drawing at the top of the screen, which isn't what we want. We want to be drawing in the bottom half of the screen. So I'm going to just cache here a little row position, which is that calculation already. So instead of drawing to this Y coordinate, I'm going to draw to the row instead. And that makes sure we're in the bottom half of the screen. In a similar way, we can draw the other types of road section. So the next thing to be drawn is the clipping board. And we're going to draw that using red pixels. I'm not going to type all of these out, but it goes without saying it looks the same for the other types of sections. So in between the left clip and the right clip, we've got road, so I'm going to draw that in as grey. And then we've got the right-hand clipping board, so that's red again, and finally going to the edge of the screen, we've got more grass. One final thing before we try this is to make sure that we erase the background first. So I'm just going to draw black empty spaces across the whole console screen, using the fill function, which is provided by the game engine. That just iterates through 2 loops until it's coloured in all of the pixels. Let's have a look what this looks like. Well, we can see that we've got the bottom half of the screen coloured in now, and we've got grass, clipping board and road clearly defined as sections. The next thing, of course, we're going to need is a car. And I'm going to add a variable to the class to store our car position on the track.
This time I want the car's position on the track to go from -1 to +1. So -1 will be on the left hand side and +1 will be on the right hand side. That means 0 will be dead centre in the middle of the track.
So we need to do some scaling to work out where that is in console space. So screen width divided by 2 will give us the middle of the track. And I want to offset from the middle of the track where we're going to put in the car. I'm also going to curiously add, because I've seen into the future of course, a -7 here. And I know that that's going to be the width of the sprite of the car. So the middle of the sprite of the car will align with 0. And this way when we draw the car, it's not going to be offset to the right. So to draw the car, I'm calling the drawString alpha function here, which simply takes any space and doesn't draw it in the background. So it pretends that that character is transparent. And I'm going to draw the car in the X position will be defined by nCarPos that we've just worked out, and the Y position is going to be fixed on the screen. So let's take a quick look at this. And brilliant, we can see we've now got a car in the middle of the road.
But something doesn't look quite right. We're lacking perspective.
Perspective isn't as complicated as you might think to implement. What we're going to do is take the current row and divide it by half of the screen, so that basically gives us a percentage. And therefore the perspective tends towards 0 when Y is small, and it tends towards 1 when Y is large, in a linear fashion. The road width variable is what governs all of the other metrics used to define our road. So if we modify the road width for any given row, everything else should adapt accordingly. Now if I just set the road width to be equal to the perspective, it probably won't look very convincing. Let's see. It does work, but our road disappears at the horizon, and it takes up all of the screen at the bottom. So we want to add some more sensible boundaries to this. I want there to be a minimum 10% of screen width. So I'm going to throw that in as a constant, and I'm not going to take 100% of the perspective, I'm only going to take up to 80% of it. So this means we have a road width going from 10% to 90% of the screen width. Let's have a look now. That's a lot better.
We need to create the illusion of the car moving forward. Of course the car doesn't move forward in the screen. What we do is change the scenery to give the illusion that the car is going forward.
I'm going to create another variable now which represents the distance the car has travelled around the track. I'm going to add in a little bit of user input to help us debug things. So I'm going to make it that when we hold down the up key, as called by this if function here, the distance is increased proportionally according to elapsed time. If we remember from other videos, the computers don't run at the same speed, so we need to take that into account when we're building a game engine. To give the illusion of forward movement, I want to draw some lines on the grass of different colours, but these lines appear to flow towards the player. We also need to take into account perspective, so I could just have lines that are all equally spaced apart and move these towards the player. However, this would lose the illusion of the perspective, which is bad. Instead, what I want is in the distance my lines to be very close together, and as they approach the player, they get further apart. We can achieve this line positioning by using some simple maths. Here, using the Desmos.com platform, I'm graphing a sine wave, but it's a sine wave that's been modified by two things. Firstly, the x direction represents the perspective, and as we can see, as the x gets larger, like it does when we're drawing it, the peaks get further and further apart. But I also need to take into account the phase, and the phase is going to be represented by the distance the car has moved around the track. So by moving this slider and changing the phase, we can see we get this nice transition. So by using nothing but a periodic oscillatory function, we can do all of this in one line. So I've got my sine here, and here I've got my x. I'm taking the cube of 1 minus the perspective here. This is a bit of fine-tuning, and we'll find with this application that actually we do need to just hand-tune some values sometimes to make it feel right. The result of this sine function will of course be between -1 and +1. So I'm going to threshold it to tell me whether the pixel should be green or dark green. And so now, instead of hard coding the value into the grass drawing routine here, we use our variable instead. Let's take a look. So that's quite nice. We can see we've got narrow, alternating light green and dark green colours far away from us, and the bands get bigger and bigger as they approach the screen. And if I hold down the up button, our distance should increase. Although at this point it's doing it very slowly. No matter, we can go into the code. And remember, this is input just for debugging right now. We'll change that to 100, so this should be 10 times faster. Let's have another go. Very nice.
We'll do exactly the same for the clipboards, but I want to use a higher frequency because I think the red and white boundaries should be closer together.
So whereas with our grass colour, our frequency was dominated by this 20, I'm going to use for the clipboard colour 80, so it should be a 4 times denser frequency. I'm also instead this time going to choose red and white colours. And we'll set this for both clipboards. Let's take a look. Very nice.
It's starting to look like a racing game.
So how do we go about defining a track? Well, in most modern games, of course, the track is a 3D model, and it may be tempting to do something similar, for example having a whole load of nodes and defining some properties between the nodes in 3D space. I propose we do something simpler than this. I'm going to break the track up into discrete sections. And I'm going to label each section with curvature and distance. And as the player moves around the track, we look how far they've travelled, accumulate the distance for all of the sections, and work out which section they're in. And all we need to display on the screen is the track's curvature. The thing with this approach, though, is it allows us to create completely nonsense tracks. But the player will never know that they're nonsense, because you can only see the curvature for one section of track at any given time. In fact, we don't even need to make the ends join together, because we can simply loop around our list of segments back to the start. To store the track, I'm going to use a vector of pers, where the first element of the per is the curvature, and the second is the distance. And we'll create our track in the onUserCreate function. And so creating a track is very simple. So here I've added a straight section because the curvature is 0, and it's going to last for 10 units. I'm going to use this as the start-finish line. So I'll just label this one separately. We'll come back to that in a bit. Then I'm going to want a nice long straight section. So again, 0 curvature, but this time it's going to be for 200 units.
Of course, units are meaningless in this. Let's assume they're meters.
After the long straight, I'm going to add in a sharp bend. So here I've got a full curvature of 1 to the right. And again, the length of this curve is going to be 200. Let's go into a nice long straight again, this time twice as long as the previous one. And we'll have a sharp bend the opposite way. I'm going to throw in a chicane here. So we've gone from -1 curvature for a short distance to +1 curvature for a short distance. Now I've got a vector full of track sections, I need to work out where I am on the track according to my car's distance. And to do this, I'm going to track 2 more variables. I'm going to have offset, and I'm going to have track section, which will be an integer representing the index of the vector. I'm going to be lazy this time. I'm just going to iterate through the vector section by section, accumulating the distances. And when the total distance is greater than my current car distance, I know to stop. I know which section I'm in, and I can work out how much my car is offset into the track. Once I know this index, I can work out the target curvature for that section of track, and I can display that now on the screen.
Displaying curvature is simply angling the track off at a particular radius.
It's a good job we have this middle point variable, because all we need to do is change the middle point depending on the perspective and the curvature of that section of the track. The rest of the drawing routines will update accordingly. So let's start naively by just offsetting the middle point by the target curvature. We know that on the straights the target curvature is 0, so the middle point stays in the middle. Or we plus or minus 1 to it as necessary. Let's see what happens now as we move forwards. So we've got a straight section, and we've got some wild curvature to the right, another straight section, wild curvature to the left. It's not very good, but we can see that we're going through track sections.
The problem here is our target curvature goes in discrete steps. This can't happen, so we need to slowly interpolate between different target curvatures to give us the impression that the road is turning left or right.
Because this is persistent between update loops, I'm going to add a variable, fCurvature, which represents the curvature of the track at a given point in time. To perform the linear interpolation, I'm going to calculate the difference by subtracting the current curvature from the target curvature and multiplying it by f elapsed time. I'm then going to update my f curvature with that difference. And instead of now using the target curvature variable, I'm just going to use the curvature variable. Let's see how this works. So I'm pressing the forward key, and we can see there was a nice smooth transition between the track section's different curvature. There was the chicane. However, it clearly still doesn't look right, and that's because our interpolation of the perspective is linear, which shouldn't be the case. Our roads need to look like they're curved. So I need to now factor into our middle point calculation the perspective. And I'm going to do this by multiplying to 1 minus perspective to the power of 3. Let's take a look. So as I go forward, we can see it bends, and we can see it continues to bend because the elapsed time is still ticking over on the game loop, even though the car's not moving forward. So we'll address that in a minute. But we can see now that the curves smoothly move around, and if we get to the next bend, what we're actually looking at here is the cubic function of the perspective, which I believe looks about right now. We don't necessarily have to use the cubic, we can use the quadratic instead. But I feel that these bends don't feel quite right. I guess it's a matter of personal taste. I'm going to stick it back to the cubic.
We just saw then that even though the car wasn't moving, the track was still moving around. So we should address this by changing how much we interpolate the track by how fast the car is moving. So if the car isn't moving, we don't do any interpolation.
It's time to add another variable, and this one is going to represent the current speed of the car. We may as well take this opportunity to also add the feeling of acceleration and deceleration. So if the key is held, we're no longer going to update the distance directly, we're going to update the speed variable. And if the key is released, we want the car to brake. We're effectively emulating drag here, so I'm going to not make them the same. This little dynamic may add some interesting gameplay later. And of course, instead of increasing, I'm going to decrease. Once we start playing with variables like this, it's always good to make sure we remain in control of them. So I'm going to clamp them here, so speed is always between 0 and 1.
After all, we don't want the car going backwards.
But we still need to modify our distance variable, so we'll do this here. And I've chosen a value 70 here, and we can play with different values in a minute, but this uses our speed variable, which will be between 0 and 1, and we're using the elapsed time again. So this should give us the feeling of acceleration. But because our speed is clamped between 0 and 1, we can effectively use it as a brake for our curvature interpolation. So in this calculation here, I'm going to multiply by f speed. So if our speed is 0, there is no change in the curvature displayed on the screen. So I'm accelerating, and I've let go of the button, and we see we slowly come to a halt, and we slowly pick up speed. Goes round, I'm going to let the car stop, and we can see that the track has stopped interpolating.
At this point I've not implemented any steering, we'll come to that next.
So basically I'm now driving like a camera around the track.
By now you're probably thinking this is all very well and good, but we've not actually implemented any game yet. All we can do is move around the track.
So how do we turn this into a game? And this is the bit where I said at the start of the video we can actually make something really mundane into something fun just by how we present it on the screen. So here is a track broken into sections. And as the car moves along the track, let's draw a little car here. As the car moves along the track, we want to follow the curvature of the track as best as possible. So we're going to have two particles. A blue particle controlled by the player, and a green particle controlled by the track curvature. So as we're going along, we're not accumulating any curvature along this straight section because it's 0. But as we go around the bend, our curvature has accumulated. It remains the same for this straight section, but again, it accumulates a bit more. We should expect the player to do pretty much exactly the same thing. So if the player is moving along the track and can achieve the same curvature as what is ideally specified by the track sections, then the player's car will always remain in the middle of the track. However, if the player starts to steer, let's for example say on this straight section, the player's curvature can change, and this will change the position of the car on the track horizontally. Let's consider this from a slightly different perspective. Let's assume we're playing a game where a path is being presented towards the player, and the player has to press the left and right key to make sure that the point remains on that path as the path is moving towards them. If the player can keep the point on that path, everything's great, good. This is the same as our car being in the middle of the track. But as the player struggles to keep the point on the path, due to forces such as acceleration, the challenge becomes more difficult. And ultimately there can be a discrepancy between where the player's particle actually is and where it should be. And it's this discrepancy which we'll use to position the car horizontally on the track. So we're going to accumulate two variables. One is the track's curvature, and the other is the player curvature. And if we subtract the two, we get our horizontal car position. Now we can use our horizontal car position, in fact we can use the absolute of it, to work out are we still on the track or have we drifted off the clipboards and onto the grass. So if we take the absolute of it and check, so we'll say horizontal car position, absolute is greater than, we'll say a value for now, 0.8. then that means we're off the track. So this line is where we accumulated the linearly interpolated curvature of the track, so we'll use the same function to accumulate the track curvature. So this variable represents the curvature of a single particle moving around the track. We'll need another variable which represents the player curvature. And this variable is controlled solely by the player's inputs. So if they use the left arrow key, we want to steer left. And likewise something similar for right. And if the track curvature and the player curvature are different by a certain amount, we want to artificially slow down the car, because this means they'll have gone off the track. We might need to fine-tune this value. But I've used a higher deceleration rate here than normal, i.e. not just accelerating, to make it feel as if that the grass is grippier than the road. We should now draw the car in a different place depending on the discrepancy between the two curvatures. So we've got our F car position variable here, so let's set that to something more useful. In this case, it's just going to be the direct difference between the player curvature and the track curvature. So if the player curvature has overestimated the overall track curvature, the car will drift towards the right. On the other hand, if the player has underestimated the total curvature, the car will drift towards the left. So I can press left, the car moves left, and I can press right, the car moves right. And that's because our curvatures are not the same. In fact, let's display the curvatures on the screen. After drawing the car, I'm going to display a whole load of stats on the screen. So I've got the total distance around the track. I've got the current curvature for the section of road being displayed. I've got the player curvature, I've got the player speed, and I've got the current track curvature. Now, given the high resolution of the console, these may be difficult to see, but let's have a look. So as I move the left key, I can see that my player curvature is decreasing, so now it's 0.5, and of course the car has moved to the left, because the overall track curvature is 0, and I'm about 0.5 here over to the right. So when I specified the 0.8, that's about there, we can see the car is touching the grass. And likewise, minus 0.8 is about there too.
So keeping the symmetrical setup from the start has proven really advantageous. It has allowed us to do collision checking on straights and curved sections with relative ease.
Now let's see what happens when we drive the car forward and come to a bend. I'm not going to steer the car. We can see there's a discrepancy between the curvatures, and that's because the car has carried on going in a straight line. And this is exactly the behaviour we want. The car now drifts towards the outside of the bend, and it effectively gets stopped by the grass. So the player has to then keep the car moving in. It also gives us this impression of inertia of the car going round the bend. So if we're going too fast, because we modulate our player position with speed, the player can't get around the bend, so they have to lift off the accelerator. And this can be shown in this nice long section here with a slight curve to it. I have to keep correcting my horizontal position to get around the bend successfully.
It's actually quite challenging to get around the track without any incidents, without any artificial slowdowns. I want to stay on the track, so I actually do have to follow the racing line.
At the moment though, we have a dangerous element of our code. If the total distance our player has moved is greater than the total distance provided by the track segments, then we're going to run out of vector elements to choose from. This will crash. To make sure this doesn't happen, we want to assume that all of our tracks are actually loops. So if we take our current player distance and we see if it's greater than the track distance, which we'll calculate in a minute, then we simply want to subtract from our player distance the track distance. So the track distance is going to need to be another variable in our class. And we'll calculate that by simply going through all of the elements in the vector and adding up the second part of the pair. Easy with the auto keyword. I need to implement some sort of indication that I've actually done a lap of the track. Now, I'm not going to go into putting furniture and start-finish sort of checkerboard patterns. That is actually quite complicated.
And I'll leave that as an exercise, along with putting other players on the track. These are interesting challenges to do using this framework. Basically, all I'm doing is rendering some geometry. There is no AI, and that might be an interesting challenge for another video, or have a go yourselves.
To give the player a visual indication that they have done a lap, I'm going to flash the road white, and I'm only going to do this when the track section that's been selected by the distance is equal to 0. It's a bit of a hack. So instead of just grey, we're going to use road colour, and the reason it's a bit of a hack is because we did specify in one of our sections pushed into the vector a very short section. So let's see what that looks like. Now we can see the road is white, and as we start driving, it's gone to the normal grey colour. And as we take this long curve along the back straight here, it should pull into a regular straight section, and then we should cross the start-finish line. And we did by seeing the road flash to white there. And we're looping back round again.
We need to indicate to the player that they're making progress, so we'll start recording some lap times, and we'll display the most recent 5 lap times so they can see whether they're getting worse or better.
Now you might think I'm going to go straight into the chrono library to do lap times, but I'm not. I don't like it. So I'm going to have a floating point variable called current lap time. And the nice thing about this approach is because the game engine itself provides the difference in elapsed time, I can just accumulate this. So here I've just accumulated the elapsed time into the current lap time. Now we can also exploit this little error checking function before to tell us when we have done a lap, because of course if the distance is greater than the total track distance, we must have gone round the track at least once. So when this statement is true, we'll use that to reset the current lap time. We should draw this information on the player's screen. But I just have a floating point filled with floating point seconds. I'm going to create a little lambda function to help me out. So the lambda function takes a floating point t parameter, which is the time in seconds, and it's going to return a w string, which is the string equivalent of that time in minutes, seconds and milliseconds. So to calculate the number of minutes, of course I just take t and divide it by 60. The fact that it gets cast to integer helps us out here. It gets rid of all of the crud at the end of that remainder. Once I know how many minutes, I can subtract that from the time and calculate the number of seconds that are left over. And in the same way, I can calculate the number of milliseconds, but I need to multiply this by 1000 at the end because this will be 0.111, whatever, but we don't want to display 0.0.0111, so we're going to multiply it by 1000 to give us a nice number for displaying as a string. And then with liberal use of the toW string function, I can glue all of this together. Once I've got my little lambda function, drawing the time to the screen is easy. I can just use the drawString command, which is part of the console game engine's library of drawing utilities. I'm going to draw it to a fixed position, 10 columns in by 8 rows down. Disp time, f current lap time. But let's not forget I want to store the most recent 5 lap times so the player can see if they're improving or not. I'm just going to include a list of floats for this. I'm going to initialize the list with 5 0 lap times. And the reason I'm choosing a list instead of a vector for this is I like the push from the front and pop from the back functions. So I'm just going to push the current lap time. This is our little lap checking function, remember? So once we've done a lap, I'm going to push to the front of the list the current lap time. And I'm going to pop from the back of the list whatever was there before. We should also display these times to the player, and having our little lambda function has made this much simpler now, because all I need to do is create an auto to iterate through the lap times, and I draw them all to the screen. I've got a little temporary variable j here because I want them to draw them line by line. I need to increment that. So let's have a look. We can see in the top left that there is a timer accumulating the current lap time. And just as I'm about to cross the finish line, we see it popped it into the list, and it's been stored, 53 seconds. Well, that's because I was doing other things with the cameras and microphones in between. I guess you always need a hot lap to start with. 34 seconds, much better.
So now we've got the fundamental mechanics of the game out of the way, the only thing that strikes me left to do is we're only really drawing to half the screen. So let's try and make the game look a little prettier.
Instead of filling the screen in with all black, I'm going to draw the top half as 2 shades of blue. This gives us the impression of some sort of sky. But I want to draw some scenery in the background that moves in proportion to how the player is driving around the track. The scenery is not going to be very complicated. In fact, all I'm going to do is use a sine wave. But as we did with the lines going towards the player, down here, I'm going to use the player's curvature now to adjust the phase of this sine wave, and that will give the impression of the mountains scrolling across horizontally in the background, but in some way it'll be proportionate to what's actually happening in the foreground. So my hill height here is simply a sine function, a particularly low frequency sine function where x is just the screen width going across the screen. And that will give me, of course, a value between 0 and 1, which I multiply by 16. So I know that my highest mountain is going to be 16 characters high. But I'm using the track curvature to offset the phase of this sine function. The rest of the code here simply draws a line from the middle of the screen to the hill height. So let's have a look how the mountains and sky go together. So on the straight here, we can see that the mountains don't move. And if I move the player character, great, because we're not using the player curvature to calculate the mountain's position. But as the track goes around the bend, we can see the mountains move too. And they stop moving when we straighten out again, which is exactly the behaviour we would want. And when we go around a bend in the different direction, they move the opposite way.
It's simple tricks like this that can create a much more compelling gameplay experience. Now the player doesn't really have to focus on the car so much, the whole screen is giving them information about what's going on. So we've got these periodic oscillatory functions giving us lines, giving us perspective, and we're using a very similar function to give us some horizontal movement too.
There's only one more indicator we need to give to the player, and that is that they are actually pressing the left or right key. But instead of just having a left or right arrow appear on the screen, I thought it would be nice to have the car trying to point in the direction that they're steering.
Or as best you can do with ASCII anyway. Scratch that, as best I can do with ASCII. I've seen some brilliant ASCII art out there, and if anybody can do anything better, please let me know.
So I'm going to create a car direction variable, which is just simply set to +1 or -1 depending on which key is pressed. So if they press the left key, it gets set to -1. And if they press the right key, it gets set to +1. And so now, instead of choosing to draw a static car, I'm going to use a switch statement with 3 different car sprites. I've just cut and paste that in. So if the car's turning right, we get the +1. It's angled slightly to the right. Yes, it looks terrible, I know. My apologies. This one looks even worse because of the escape character being part of the ASCII model. Let's have a look. So now we can see the car changes direction, and it's a little bit more fun.
And so that's that. It's about 200 lines of code in total. What I think is the essence of this video is how simple some of the functions and routines have been to give us quite a complex looking behaviour. For example, we've been able to give the illusion of moving forward just by choosing the correct mathematical function. And the game itself is simply the difference between 2 numbers changing in time, and the player has to try and keep that difference as minimal as possible. I just like how when you present this information in a particular way, you can get a game out of it. As always, all of the code is available on GitHub to download. Have a look at the links below. I've also noticed a recent surge in subscribers, so I'd like to welcome all of the new people to the channel. Please check out some of my other videos. None of them need to be watched in any particular order. If you've enjoyed this video, give me a big thumbs up, have a think about subscribing, and I'll see you next time. Take care.